to the session to our chairman, Professor Aditi Shende from HRI. So, Professor Shende.
Is she there? I don't see her.
Excuse me, I'm from HRI.
Yeah.
I think there is a problem here with our internet. I've tried to connect from the phone. I'm not sure how it will work. Our entire internet is down for the institute, so maybe she hasn't been able to join.
So shall I just start then?
Maybe.
Yeah, I guess you asked the organizers.
Who is any of the organizers there?
Let me check. Priya is there. Priya Mahadevan. Yeah. Okay, let me check. Yeah, maybe you can start in the meantime.
Okay, bye. See you.
Priya, shall I start?
Just a sec, yeah. Sorry, there was some confusion because,
Priya, I can't really hear you.
Okay, am I clear now? Am I audible?
Yeah.
Okay, sorry, there's been a lot of confusion because both the chairperson and the second speaker are from HRI. And,
okay.
And they have internet problems over there and
okay.
they're unable to join. So we were just trying to see what to do. I'm sorry about the delay. So we can, I think there are only 17 people. Should we wait a little bit because everyone seems to be a little slow to this morning? We'll just see.
Yeah. Maybe it's better if I just start, no, Priya?
Okay, all right, because I thought, okay, fine.
Okay, I'll start.
Yeah, so yeah, good morning, everybody. Welcome to this to the fourth day of the meeting. Listen, I guess we are losing a few people because of internet connections, but hopefully they'll be able to join later. So I request Shobhana to give the first talk of the day. Yeah, Shobhana. I'll warn you at 25 minutes. 20 minutes.
Yeah.
So that it leaves you with 5 minutes for talk time.
Okay.
And 5 minutes after that for questions. Yeah, go ahead.
Okay. So you can see my screen, right?
Yes.
So I will be talking today about diffusion barriers and growth pathways and scaling relations for small metal clusters. I thank the organizers for asking me to give this talk. So the work I'm going to present was mostly done as part of a PhD thesis by my student Nisha Mammon, and it was published last year in the Journal of Chemical Physics. So I'm going to talk about small metal clusters and why are we interested in them? We're interested in them because they're good nanocatalysts. So nanoparticles of precious metals are supported on oxide substrates and they're used in many contexts. For example, in the catalytic converters that are used in cars, which convert things like carbon monoxide to carbon dioxide. And because of this, there's in fact a big rise in the thefts of the catalytic converters because they have these small quantities of these precious metals whose price has been rising hugely recently. So because I've been working in this field, I've started watching the price of precious metals. And though there are huge fluctuations in these prices, which I've shown you in these graphs, for example, platinum and palladium, and this is gold, silver, palladium, etc. The percentage rise, you see there are huge rises over time. You know, I mean, these are like 5,000% rises and things. And just as a curiosity, I'm showing you that these prices, they were somewhat sensitive to the coronavirus. So there was a dip in the price in March, but then it recovered pretty fast. So they are extremely expensive. And so one is interested in studying how these work and can we make them better, etc. Now, it is generally true that if you look at the catalytic activity of these particles, then the catalytic activity rises sharply as the particles become smaller. So what is plotted here is the activity for CO oxidation of gold nanoparticles. And you see as the particle sizes become smaller and smaller, the activity rises sharply. So one is interested indeed in very small nanoparticles. Okay. And in fact, you are even interested in single atom catalysts. So this is nice for us who are computational physicists because those are, of course, the easiest to study. So even one atom, two atom, three atoms of these small clusters are of interest to us because they can be effective catalysts. For example, here is a news item from CNE News saying that single atom platinum catalysts can be used to generate hydrogen from methanol. However, there is one problem, which is these very small atom nanoparticles are unstable to what is called sintering. That is, it is unstable for smaller particles. Smaller particles are not energetically stable. They can always reduce their energy by coming together and forming larger particles. So here I've shown, for example, for platinum, if you increase the number of atoms in a particle, in a platinum cluster, the energy is always lowered. It's lowered and lowered and lowered. And here it's up to 100. But this is a general trend. As you increase the number of particles in the cluster, the total energy keeps going down. It is always favorable to form a larger particle. So here are two videos which show the processes in which this could conceivably happen. So the video on the left is an electron microscopy video, which is actually showing gold nanoparticles on a surface, and they're diffusing as entire nanoparticles, and their particles are migrating and coalescing. I will let the video run for a while and you'll see these whole particles are migrating and coalescing. I couldn't find a similar video, which was an experimental video for the other process, which is of interest, which is what people refer to as Oswald ripening, though it's not quite Oswald ripening. It's a process of monomer addition. So this is a molecular dynamic simulation, which shows that single atoms are diffusing on the surface, and then they're joining larger islands, and slowly the particle is growing.
Shabana, we cannot hear you.
It said the host muted me. I didn't mute myself.
Sorry. That was, I was trying to mute some of the other people. It like moved fast. I'm sorry about that. Yeah.
I'm all right. So I couldn't unmute myself.
Yeah. Okay. Sorry.
All right. So if you were watching the video, you would have seen that okay. So those were the processes by which this process of sintering can happen. So we're interested in preventing this. So the first thing we want to know is, so we are interested in studying these ultra small clusters of metal nanoparticles on an MgO substrate. And the elements we're studying are platinum, palladium, gold, and silver. And we're looking at whether the surface might be defect-free or it might have what are called F centers, which are oxygen-based species. And because we're interested in studying this process of sintering, we're looking at diffusion barriers, mechanisms, size dependence, trends across elements, growth mechanisms, scaling relations, the role of defects, etc. And these are pretty standard density functional theory calculations. The only slight thing of interest might be that the diffusion barriers are calculated by what is called the nudged elastic band method. So let me first give you the DFT results. So the first thing we find is just the absorption energy. So these are the strength by which these small nanoparticles are bound to the surface. So the top row shows platinum nanoparticles bound to a defect-free surface, and the bottom row shows the same nanoparticles bound to a surface with an F center, which is an oxygen defect. The position of the missing oxygen atom is shown by this yellow sphere in the bottom panel. And you see that if you have this oxygen defect, then the strength of binding increases. And this is important because if it is bound more strongly, then it is less likely to diffuse and to get sintered. And so it is favorable to have these oxygen vacancies on the substrate. Now, the absorption energy, this is the same thing. It is shown now the trends as a function of cluster size. So this is this binding energy of the cluster to the substrate. On the left, it shows it when there's a defect-free surface. On the right, when there is a defect. And you see that the binding is stronger, but also interestingly, the size-dependent trends seem to flip when there is a defect. Now we are studying diffusion. Now, diffusion, the interesting thing, okay, there's a lot to see in this chart. I have listed two things in this chart. One is the mechanism by which the cluster moves along the surface, and the other is the diffusion barrier. I will discuss this more. But the important thing is that the mechanism by which the cluster moves is not always the same. It depends on the element. And also the barriers by which they diffuse are very element dependent. So what are these mechanisms? Let me show you. So if you have a monomer, there's only one mechanism. That is a single atom of the metal on the substrate. It can only move by this process, which we call hopping. And you can calculate the diffusion barrier for this. This shows, for example, on the bottom panel, I've shown you how the diffusion barrier looks. There's nothing very surprising there. The interesting thing comes when you look at the larger sizes. So for example, if you look at a dimer, it doesn't move by a simple translational motion. Instead, it flips. Okay, so this is a cartwheeling motion. And you look at the energy landscape and it's a little bit complicated. Okay, now this is for platinum. I'm only showing you examples for platinum. For the trimer, it does this weird sort of moving motion. And when I saw this, I kept thinking, this reminds me of something, this reminds me of something. And then finally, I realized what it reminded me of. In this movie, Star Wars, I don't know how many of you have seen these Star Wars movies. There are these weird machines called AT-AT walkers, and they move along in this slow lumbering fashion. And the trimer of platinum moves like that. And the tetramers do yet another kind of motion, which is this funny rolling motion. And these motions all have consequences, which I will discuss. So now, just from these DFT results, it turns out you can get an awful lot of information about how these particles will behave. So we're going to milk these results for all they are worth. So, okay, so you may say, okay, is there a size dependent trend for platinum? Not very clear. And then you look at gold and it looks no trend at all. And you look at all the elements and you say, this is one big mess. And it looks like there is no element dependent trend. And it looks like you can't really get any fundamental understanding out of this. But that's not quite true. So I put this quotation from Shakespeare here, that though this be madness, yet there is method in it. So to to look for scaling relations in these diffusion barriers, the first thing we were inspired by is there's something called the Huttig temperature, which is if you have a metal surface. So this is not a cluster of a metal on an oxide substrate, just a metal surface. Empirically, it's known that there's something called the Huttig temperature, which is that if you reach roughly 1/3 of the bulk melting temperature for that particular metal, that is when the surface, the atoms on the surface of the metal start becoming mobile. So we wanted to see if there's any similar statement for the sintering temperatures for metal nanoclusters on MgO. Okay, so we're plotting these diffusion barriers versus the melting temperature. And it looks like you have a pretty good scaling for the monomers, the trimers, and the tetramers, but you don't get such a scaling for the dimers. Now, when we first said this, everyone we showed these results to said, no, this is really weird. Why the hell should the diffusion barrier of a small metal atom or a small metal cluster on MgO be related to the melting temperature in the bulk? And we had howls of outrage from the referees as well. But I'm going to try to convince you that, in fact, this is a meaningful correlation. And I can also explain to you why we don't have this correlation for the dimer. Okay? So let's look at it step by step. So the first thing is that the diffusion barrier correlates with the binding energy of the cluster to the substrate. You see this correlation very clearly for the monomer. You see it for the trimer, except maybe palladium goes a little bit off. And for the tetramer, it's an excellent correlation. And certainly it seems to be true that the silver comes first, then gold, then palladium and platinum, except for the dimers. So can we understand why? It turns out there's a very simple explanation for this. And incidentally, it's really surprising, okay? For the tetramers, you have this wonderful straight line, even though the tetramers move along the surface by different mechanisms, okay? So I had shown you the platinum tetramer moves on the surface by rolling mechanism, but silver moves by different mechanism, gold moves by yet another mechanism, and still you get this excellent correlation. Okay, so this is a sort of simple hand-waving explanation. When a cluster moves on the surface, you can approximate its, if you can approximate its energy landscape by a superposition of parabolas.
Okay. So when you define a variable of character, normal character, 8 bits of memory or 1 byte is allocated in the memory.
What is someone asking a question? I couldn't hear what someone said.
I think it was somebody who had them who was unmuted and talking.
Okay.
Okay.
All
sorry
right.
about yeah.
Okay, so if you can approximate it by parabolas, then okay, so the height, the diffusion barrier is given by this value, this purple arrow here, and the binding energy is given by the depth at the bottom of the parabola. And from this figure, you can see that if the binding energy becomes more, that is the depth becomes more, the diffusion barrier also becomes more. But this argument works only if the energy surface between the global minimum and the transition state is approximately parabolic. So let's look at our energy landscapes for the diffusions for platinum as an example. So for the monomer, it was approximately parabolic. So that's fine. And we got the correlation. For the dimer, it is not parabolic, notice it, because you have this extra minimum. And we did not get the correlation. For the trimer, again, it is parabolic. So we got the correlation. And for the tetramer, it's approximately parabolic. And again, we got the correlation. So we understand why we got the correlations in 3 cases, and we did not get it in the case of the dimer. Now, the cluster binding energies correlate with the cohesive energies of the bulk metals. This makes sense because you have these interatomic bonds, and when you break some of them to form the cluster, then they want to compensate for that, and so they form bonds of similar strength with the substrate. So this is shown here. You see that in all cases that correlation holds. So again, if the cluster binding energy correlates with the cohesive energy, and then if the diffusion energy correlates with the cluster binding energy, then the diffusion barrier will correlate with the cohesive energy, except in the case of the dimer for the reasons I have already discussed. Okay, now for the bulk metals, it's a well-known result in the field of sort of condensed matter that the cohesive energies correlate with the melting temperatures of the bulk. This follows from something called the universal bulk binding curve. So this shows this correlation. But incidentally, it is also a well-known result that palladium falls slightly off this curve. So I've shown you that the diffusion barriers correlate with the binding energies. The binding energies correlate with the cohesive energies, and the cohesive energies correlate with the melting temperatures. And so the diffusion barriers correlate with the melting temperatures, which is what I wanted to show. So I hope I've shown you that this is a reasonable argument. Can we show similar correlations for self-diffusion, that is clusters or atoms of a metal on that metal surface? So here I've shown you for single atoms of the metal on the 111 surfaces of these metals. And you see that this correlation holds pretty well, again, for similar reasons. And we can try then to get a mathematical relation that relates the temperature at which atoms become mobile on that surface to the melting temperature. And we get this relation that I have boxed. You get something like this empirical Huttig term, but you have an extra coefficient in front. So we have also made reasonable, we've rationalized this empirical finding of this Huttig term. Okay, so now in the remaining 5-6 minutes, I want to—
5 minutes of talk time.
Yeah, so I want to explain something about the growth processes. So for the growth processes, how these clusters grow, we need to look at the energy gained by sintering. That is, how much is the energy lowered by when two clusters of a certain size come together to make a bigger cluster. So let us first look at, here I have shown the energy. For example, look at the upper left panel, when two platinum atoms come together to make a platinum dimer. And then I have compared it with gold, with palladium, with silver, etc. Incidentally, here the interesting things are you find that thermodynamics and kinetics give you different answers. Because for thermodynamics, you look at how much the energy is lowered by. For kinetics, you look at the heights of the barriers. Okay, and incidentally, there's something known as the BEP relation, which says that these should both give you the same answers. And in these cases, that is not true. And that is because the transition states for these processes look very different from the final states. And that's because of these strange motions that you have. Now, for how does the trimer form? That's the simplest process we can look at. It could happen in one of two ways. You could have a single atom diffusing and joining a dimer, or you could have the dimer diffusing to join the monomer. Now, intuitively, you might think the above process should be lower in energy than the one below, but in fact, it is the other way. It is more energetically favorable in the case of platinum for the dimer to diffuse, because in the case of platinum, monomer diffusion is a very energetically unfavored process. However, in the case of gold, it is the other way around. Okay. So now we can start looking at the same thing for all the metals. So it is very metal dependent which of these processes is more energetically favored. Now we can start looking at it for one more step for the tetramer to form, for example. And then you find, okay, so you look at it step by step. So let me do here a comparison of platinum and gold. And you see that here for platinum, the cluster is growing by one atom being added at a time. So it is a monomer addition process, but it is in a very unexpected way. Usually you expect that when you have monomer addition, it is the single atoms that diffuse and join up with the larger cluster. That is what happened in the video I showed you right at the beginning. But here it is happening by the opposite process. It is the larger clusters that are diffusing and joining the single atoms to form larger clusters. Whereas in gold, something quite different is happening. In gold, it is growing by particle migration and coalescence. So these clusters are diffusing and then they're forming larger clusters. So all this information we're able to get just by looking at the diffusion barriers. So it's very rich, the amount of information you can get from the DFT studies we have done. So you can look at this for all the different elements we have studied. It's too much information here for you to take in. So I'll just tell you that it is very metal dependent what happens. We can also look at the effect of defects. Okay, so sintering becomes less favorable when you have defects, which is what you would intuitively expect. And you can, this is true for all sizes. But again, it is for a counterintuitive reason. I mean, because the diffusion is happening, the diffusion barriers are the same, but there are clusters that are being pinned at these defects. And then the lowering of energy when you go and join a defect is, so it's a thermodynamic rather than a kinetic reason, which is disfavoring sintering when you have defects. So I'm done. So we've studied ultra small clusters of precious metals on MgO, and they diffuse by very non-trivial mechanisms like rolling and cartwheeling, etc. And I've shown you that the diffusion barriers scale with the bulk melting temperature if the energy profile is approximately parabolic. This was something that people didn't realize before our work. And I've justified why this happens. And I've also been able to explain this empirical result of this Huttig temperature where clusters become mobile for self-diffusion. The sintering mechanisms are metal dependent and F centers hinder sintering. And of course, the questions are, will this hold for larger cluster sizes? Will it hold for other metals? What about substrate orientation? And it would be interesting to feed all these results into a kinetic Monte Carlo code and do the simulations. Thank you. I'm done.
Yeah. So yeah, thank you very much for a very nice talk. So there are two questions. I think I'll ask Tanushree first to unmute herself and ask the question. Tanushree, are you there?
Yeah, I'm there.
Yeah.
So Shobana, I have a couple of questions.
Yeah.
This question is, when you showed as a function of cluster size, the sintering goes on and how the energy varies.
Yeah.
Those were done, of course, without passivation.
Without what?
Passivation.
Yes, yes, of course.
So in reality, of course, when you synthesize these small clusters, there is a big role of the passivation and also the solvent you are using?
Not necessarily. I mean, you can have ligand passivated clusters, but there are also many cases when you don't have these ligands and you don't have passivation.
Because one way to kind of arrest the growth of this cluster to bigger
Yeah.
cluster is to use the passivating atoms.
Yes, but the problem is when you passivate, you often also lose reactivity.
Mhm.
So you would prefer not to passivate in most cases, though there have been some very recent studies which show that there are some special cases where the ligands can promote reactivity, but in most cases, the ligands lower your reactivity. So for us, it is of interest to study these cases without the passivation, without the without the ligands present.
Okay. The second question is with your metal dependency. Uh,
Yeah.
so what makes the platinum different from gold and for silver? So was relativistic effect, especially the scalar relativistic effect, included in the calculation?
So scalar relativistic effects are there, but not full relativistic effects.
Mhm.
We do not believe that for these kinds of properties, the full relativistic effects are important.
Mhm.
So I think,
Scalar relativistic will be.
I mean like spin orbit or something, I don't think is
No, no,
important.
I meant scalar relativistic.
Yeah, scalar relativistic is of course there. And so what really seems to be important is just the strength of the interatomic interactions.
Mhm, mhm.
Because we are finding, as I said, that in general, things are scaling with the bulk melting temperature, which is the very surprising finding. But as I also showed you, it also depends on the mechanism of diffusion
Right.
and the energy landscape, which is, of course, a much more complicated question, and why the different metals diffuse with different mechanisms, that is a much more complicated question for which I don't have a simple answer for why different metals diffuse with different mechanisms.
Okay.
I mean, that obviously depends on very fine details of the interaction between the metal and the substrate.
Yeah, I mean, it would be
Could
good,
we
for
go to the
example,
next
if you
one in the
say
interest
that
of
other
time?
metals,
Tanushree, can we
kind of classify which metals diffuse in which way? I mean, then probably that can give rise to some understanding.
Yeah.
But I think there are other questions. So
Yeah,
I'll.
yeah. So is Arindam there? Then you can unmute yourself and ask your question.
Yes, I'm there. Shobna, can you hear me?
Yeah.
Okay, great. Enjoy the talk. But the problem is Tanushree stole my first question because I think it's very important to understand any effect of passivation on the, both sintering as well as the diffusion of the nanoparticles, especially when you're talking about such small nanoparticles. It's extremely difficult to see them stable without a passivation. So I can certainly tell you that this passivation is far more common than uncommon. So so that question has already been answered. Your calculations do not consider any form of passivation so far.
No.
The second question is whether the shape of the nanoparticle clusters, particularly when you go to very low number of atoms, whether that makes a difference in terms of both sintering or diffusion barrier lowering or
It
diffusion barrier.
absolutely makes a difference. And in fact, let me see if I can show it somewhere. We actually find the shape is even fluxional in the sense that during the process of diffusion, the shape can change. So you might be able to see it here for the tetramer. Okay, so if you see the tetramer, there is actually some change in the shape of the particle while during the process of diffusion. And if we took a different isomer, we would get a different diffusion barrier.
Right.
But I think so, but our arguments are so general that the scaling relation should work unless the energy landscape changes. So this is something we haven't checked. So this was again a surprising result for that reason. So we have to check for different isomers. That is something we haven't done.
All right, good. Thanks, Shobna.
Yeah, and yeah, there's a comment from Professor Bhaskaran which you could read in the chat box. I don't know whether he wants to add anything to it.
So, no, Shobna, I have just a brief question.
Sure.
It's a fascinating talk. I didn't know that diffusion is so complex and rich. So I just wanted to ask, you said that there's a connection to bulk transition melting temperature.
Yeah.
Can it be translated into Lindemann criteria? Because that seems to be a natural way because things may expand more.
Yeah, but so, I mean, that would certainly be one approach to it, except that, I mean, here we haven't looked at thermal properties at all. And that's a rather complex question in the sense that the thermal properties are usually, it's a quite controversial question. For example, for certain metals, the interatomic bonds seem to get stiffer as you make the clusters smaller. And for some metals, they seem to get softer as you make them smaller. And so the vibrations, like if you were to define like a cluster melting temperature, it is quite a controversial question about whether the cluster melting temperature becomes lower or higher when you go to the small cluster size. This is something I have worked on separately. But certainly that would be an alternative way to look at it. But then, of course, you have to look at the vibrations of the clusters. And we didn't go down that route. It is possible that that may be an equivalent way to look at it.
Thank you, Shobana.
Yeah, thank.
But certainly when you're looking at the parabola and stuff, but then you would look at the curvature of the parabola rather than the depth and the height. And that would be certainly an alternative way of looking at the scaling. And I wouldn't be surprised if that also scaled. Because when I look at these parabolas here, I have been talking about the height and depth of the parabola. If you looked instead at the curvature of the parabola, then that would give you something similar to the Lindemann criterion.
Thank you.
Yeah, okay. So thanks, Shobna, for an interesting talk. And now I think the organizers would like a photo session. So please.
One sec, I have to stop sharing my screen.
You have to stop sharing your screen, and everyone should start their video. Can everyone open their video and what is, yeah, okay. Who's taking the photograph? Sanjay, is it done?
Sanjay,
I didn't do my makeup, but it's okay.
Okay, let me do it.
Is it okay if we unmute ourselves?
Yeah, I guess so. Who's doing it? Manoranjan, who's doing it?
Ma'am, it's me from SN Bose.
Oh, okay, Deblina, yeah.
Deblina, yeah.
So, is it done?
No, ma'am, just please hold.
Yeah.
So everyone kindly switch on your camera.
But you're the one who should open your video. What are you doing?
This computer doesn't have the camera.
Oh my.
So actually, I another one where I have already given the presents. I mean, my attendance.
Fine. Are we done?
Arindam, are you in a car?
Sorry.
Yes. I was so desperate to listen to you, Shobna.
Yeah.
I think underlying words in this
it's done.
Done. Thank you. Yeah. So we sorry about the delay in today's session. I mean, we didn't have any problems on the other days, but today. So may I ask everyone to please stop their video? And yeah, so the next talk will be given by Prasenjit Sen. And let's hope your connection is stable now, Prasenjit, so that you can...
Let's hope so. I'm not sure. I mean, the main internet is not working. I'm relying on my 4G connection. So let's hope it holds out.
Okay, good.
But if it's too disrupted, I mean, it gets disrupted too often, just let me know.
Sure. So you can start, and I'll let you know at 20 minutes that you have 5 minutes of talk time.
Just give me a second to start this. Yeah, can you see my screen?
Yeah, I can see your screen.
Okay. So this is what I'm going to talk about. We have been exploring these layered ternary trichalcogenides for both from fundamental and applications perspective. So this talk will be about applications. I won't get into the fundamental studies here. So let me start by straight away getting into what sort of materials these are. Somehow there's a problem with my screen. My screen is stuck here.
Okay.
Okay. So these are ternary compounds with the general chemical formula MAX3, where M is a transition metal atom, A could be one of silicon, germanium, or phosphorus, and X is a chalcogen atom, sulfur, selenium, or telluride. So 3D compounds are layered, as the title of my talk suggests, and different compounds can be, in one of these two structures. So the stacking of the successive layers are different in the two structures, but the structure within the layers are the same. And here we will be concerned about only single layers of this. All right, so let us take a closer view of the structure. So this is the top view of a single layer. So the metal atoms form hexagons, as in a carbon atoms in a graphene sheet. And the centers of the hexagons are occupied by A2 dimers. And then each A atom is bonded to 3 chalcogens. See the side figure, and each of the metal atoms also has 6 chalcogen neighbors. So that is the structure. And so so when we started looking at these compounds, we asked how many of these compounds are known. And we checked ICSD, and it turns out there are 13 such compounds in layered structure that are reported in ICSD. As you see, the top 10 are magnetic insulators, and most of them are antiferromagnets, and a couple of them are ferromagnets, and the bottom 3 are non-magnetic. And we will, in our study, we will include the top 10 here, and we did not look at the bottom 3. And when I say antiferromagnet, they can be in 2 different types of antiferromagnetic order, the usual nail order on a hexagonal lattice, and something called a type 1 order, where you have ferromagnetic chains coupled antiferromagnetically. But that, those details will not be the focus of the study. So what is interesting about these compounds? Well, firstly, fundamental. They are easily exfoliable. And this paper in ACS Nano showed that many of these compounds are, the bonding between the layers is even weaker than what you have in graphite. So this dashed line over there is for graphite, the exfoliation energy. And many of these are below that. So they can be easily exfoliated into few or single layers, and they have been. On the other hand, 2 or 3 years ago, this paper in Nature talked about ferromagnetic to paramagnetic kind of transition in I guess, down to bilayers of one of these compounds, chromium, germanium, telluride. So that generated a lot of interest in the fundamental properties of these systems. But as I said, we will not focus on the fundamentals here. Our focus will be more on applications. I cite three of these here. So the top one talks about synthesis of sulfide compounds of this class and their lithium and sodium storage properties, which would be important in battery applications. And the bottom two is what sort of got us started on this path. And if you can read these highlighted texts, the left one says, in terms of catalysis, nickel phosphorus sulfide, cobalt phosphorus sulfide, and bismuth phosphorus sulfide show highest efficiency for hydrogen evolution reaction. And our focus in this talk will be on hydrogen evolution reaction. And the right one says FePaC3, the sulfide compound, and MnPaC3 yielded the highest efficiency for hydrogen evolution reaction. So we will be studying, properties of these or efficiency of these compounds in hydrogen evolution reaction. So more about that as we go along. So what did they actually study? So these are very typical, the top plot is from one of those papers. It's a very typical what is called a linear voltammogram. There's some noise in the background. So basically what this shows is that so basically the reaction that is happening is electrocatalysis of water, breaking of water in an electrolytic cell. And the question is how much voltage you have to apply to the cathode so that hydrogen starts evolving. And platinum is known to...
Please mute everybody else but the speaker, please.
Platinum happens to be the most efficient catalyst as the cathode in this reaction, and this brown curve to the extreme right is for platinum. It shows the highest current for the smallest voltage that you require, and this after that this the red curve is for MnPs3 and the yellow curve is for ATPs3. We are not looking at the sort of compounds containing 4 sulfurs, so we will focus on MnPs3 and ATPs3. And the same information is given in the right, and what is called onset potential, how much potential you need to have a certain current density. And platinum is the best, followed by nickel and cobalt phosphorus sulfide. This is for the...
Shreyasi Das, could you please mute yourself? Yeah, sorry, I'm sorry about it. Yeah, please. Have I muted?
Okay, thank you.
I'm sorry about it.
The next one is the similar experiments with the selenide compounds, and as you see, platinum has the lowest onset potential, followed by MnPaC3, FePaC3. So these are what was demonstrated in the experiments, and these are good news because one is looking to replace an expensive metal and rare metal like platinum to have efficient catalysts. Okay. So more recently, experiments were done. This is from a group in IISc, Professor Sampath's lab. And they are also, here also they show that few layers of FePaC3 or FePaC3 on reduced graphene oxide also act as good catalysts in hydrogen evolution reaction. So that's good news. But what we asked is that, only 13 of these compounds are sort of reported in ICST in the layered structure. But when you think about it combinatorially, there are many other possibilities. So are those compounds stable? Can they be synthesized? So what we did in this is that we took these 6 transition metal atoms, these chalcogens, and these carbon, silicon, and germanium and phosphorus as the middle atom to synthesize all possible compounds. compounds. And if you count the numbers, you will find that there are 72 compounds that are possible. And we basically studied all of them for their efficiency in hydrogen evolution reaction. So finally, what is hydrogen evolution reaction? Basically, as I said, it's the cathodic half reaction in an electrocatalytic water splitting. So you apply voltage across two electrodes, and the H plus ions present in the solution move towards the cathode, take up electrons, and get evolved as H2 gas. And the detailed mechanism is considered to be this, the figure on the right-hand side. The first step is that one H plus comes in, takes up an electron, and gets absorbed as H. The second step could be one of the two possibilities. Two adsorbed hydrogens could combine, form H2 and get dissolved, or one incoming H plus can take up an electron and without getting adsorbed can combine with a previously adsorbed hydrogen, form H2 and get dissolved. So these are called Polmar, Tafel, and Herovsky steps. But the main point is that hydrogen adsorption is essential. And so when one is trying to find theoretically the efficiency of a material for hydrogen evolution reaction, what one looks for is what is the hydrogen. So basically, one is looking for a simple descriptor, one quantity which will give you an indication that how good a catalyst it is going to be at the cathode. And experience shows that the simplest descriptor one can use is the hydrogen adsorption free energy on the surface. So delta E adsorption is just the adsorption free energy that you can get out of your DFT calculations, for example. And then you add the 0 point energy and the entropy different terms, and you get the adsorption free energy. So the argument is that if delta GH is far too positive, then the hydrogen doesn't like to adsorb. On the other hand, if it is large and negative, then it is very strongly bound, then it is very difficult to desorb it. So you would want to have a situation where delta GH is as close to 0 as possible. In fact, the plot on the left-hand side shows, and these are what are called typical volcano plots in catalytic reactions. So this is calculated delta GH for hydrogen adsorption on various metal surfaces versus experimental current density at some definite voltage. And as you see, the best catalysts are the sort of noble metals, which fall around delta GH equal to 0 and show the highest current density. And what I would like you to notice from here is that even delta G values, close to 0.2 is good in the sense that those metals also show pretty good activity. But platinum is the best. All right, so what do we do here? What we do here is that we screen all the 72 compounds using standard DFT calculations, which I'm not going to describe. So what we do is we combine, so we loop over the chalcogens, then the central atoms, A atoms, then the transition metals, and for each combination, we form these compounds. First, we ask, is it reported in ICST? If yes, then we take a structure of one layer of these from ICSD structure. Else, we take as our initial structure the converged structure of the previous compound. In either case, we re-optimize this structure, both lattice constants and the positions of the atoms in 4 different magnetic states: the non-magnetic, ferromagnetic, male antiferromagnetic, and type 1. And then we compare the energies and find out which one is the lowest energy state. And then we calculate formation energy of that material or in that configuration with respect to the isolated elemental solid phases. If the formation energy happens to be less than 0, that indicates that the material is thermodynamically stable. If it is not, it is discarded. And if it is found to be stable, then we adsorb hydrogen at various sites on this layer and calculate delta GH, and so on. It goes for all the 72 compounds, and the point here is that it is all done in one go. Okay, so it's not like you do calculations for 288 different situations. You just submit one job and you get your results in the end. Okay, so how are we doing on the known compounds? As you can see, the lattice constants and the magnetic states are reproduced well for the known compounds, except this one, cobalt phosphorus sulfide. We still end up getting a ferromagnetic state. Now, I cannot get into the details of this, but we have a work. I mean, you see the reference below, in which we have discussed how to describe the correct magnetic ground state of some of these compounds in DFT. So cobalt phosphorus sulfide is something we still need to explore more, but the others we are able to reproduce correctly. And just to let you know that prior to this, there were a couple of papers, at least in the literature, which failed to describe the correct magnetic ground state of these compounds. All right, so here is a pictorial depiction of what we have found. So each point here is one of these compounds. The colors indicate which chalcogen they contain, and the sign, the shape of the symbol tells you which metal atom it contains on the delta GH versus formation energy plane. So we will be interested in compounds that are below delta formation energy of 0, and we choose this small window of minus 0.3 to 0.3 EV for delta GH to find out which materials could be promising catalysts. And that is sort of blown up on the right. So if you count, there are 13 such compounds within this window. So we have 13 compounds that look promising for, as catalysts for hydrogen evolution reaction. So these are those 13 compounds. They all have, of course, negative formation energy and delta GH within the range minus 0.3 to 0.3. And some of them, nickel silicon sulfide, iron carbon sulfide, for example, they look very, very promising. Okay, so, but what I want to point out here is that none of these compounds, so these are all unknown in the sense that they are not reported in ICST. So that is good. So which tells us that there could be as yet unknown compounds that are promising catalysts. But now, in a while, I'll come to the known compounds. So another way of looking at things, all the sulfide compounds we studied turn out to be thermodynamically stable, and 37.5% of them turn out to be catalytically promising. And similarly, for selenides, about 87% are stable and 14% seem to be catalytically promising. Tellurides, they are less stable, 46%, and only one of them turn out to be catalytically promising. All right. So what we learned so far, there are quite a few trichalcogenide layers that could be, promising catalysts right on their basal planes. Are these also dynamically stable? Would they be stable in alkali and alkaline medium? These are things we are still exploring, and it will take us some more time to make definite statements on that. So these results have been published in this paper. Okay, now what about the known compounds? What about iron phosphorus selenide, manganese phosphorus selenide, and the cobalt and nickel sulfides? As it turns out that cobalt and nickel sulfides turn out to have the lowest delta Gs among the known sulfides, but they are nowhere close to 0. It's 0.8 and 0.9. On the other hand, manganese and iron selenides turn out to have some of the largest delta G values. So the question is, why this discrepancy with experiments? After finding this, we looked at the experimental papers more closely, and what we found was that so this is a statement from these papers, that all of the materials present a characteristic structure of the bulk materials with stacked sheets of varying thickness. Now, when you have stacked sheets of varying thicknesses, you of course have edges exposed. And then also they show that there are large amounts of oxygen and carbon impurities in the sample. So, but we don't haven't as yet addressed the question of impurities. But when we looked at this possibility of edges being there, we also around the same time figured out the story of MOS2 from literature. So for many years, MOS2 was believed to be inactive for hydrogen evolution reaction because the delta GH on the basal planes was found to be quite large. But DFT later, motivated by some observations on some enzymes, showed that 101 edges exposing molybdenum have very small delta G, almost close to 0. And subsequently, MOS2 was synthesized on black carbon, which exposes these edges, and they were found to be some of the best HER catalysts apart from platinum. So could that be the story with trichalcogenides also? So for that, what we do is we study the catalytic activity at the edges of these compounds. Now, I cannot describe all the details, but if you look at the structure carefully, you will find that you can cut it along these 5 lines that are indicated on this figure, and to create different nanoribbons, always maintaining the stoichiometry in your structure. So there are 5 possible nanoribbons that one can create. So they would look like this. These are the 5 nanoribbons that you can create.
Prasenjit, we have 5 minutes of talk time.
Yeah, okay, thank you. So what we do is, first, of course, we calculate the energies of these 5 structures. And in every case, it turns out that structures 2 and 3 turn out to have the lowest energy. They are close to each other, whereas the other structures have higher energy. So subsequently, we focus only on these 2 structures, structures 2 and 3. So what we basically do is that we identify possible sites at the edges where hydrogen could be adsorbed, and then go ahead and adsorb hydrogen and calculate the delta GH for the planes. So I'll show you. So basically, I have 4 different compounds in 2 different structures. So there are 8 nanoribbons and many different possible sites on each of these. So I won't, of course, explain all the details of what we see, but I'll try to convey the essential picture that we have found from this. So, so here you see adsorption of hydrogen on the what we called ribbon 2 for MnP-Sc3, and I have indicated this in green color. So X2 site at the lower edge has a delta G which is very close to 0. On the other hand, there is another site A1 close to the central atom, phosphorus atom, where the delta G value is large and negative. So basically, what this, our sort of understanding of this is that when the hydrogen concentration is low, they are far apart. So X2 sites would be acting as the catalytically active sites. But when you have a larger concentration of H+, some of them would get absorbed at E1, and then they would be difficult to remove. So what happens in that case? Because they are not that far apart anymore. So what happens is, in order to answer that question, we calculate delta GH for the second hydrogen when one hydrogen is already adsorbed at the A1 site. And again, you see there are, promising sites where the reaction can go ahead. This is for nanoribbon 2. You get similar picture. There are X1 and X2 sites which are promising when the concentration would be low, but at high concentration, A1 site would get occupied by a hydrogen, but then in presence of that, you have the X1 site which could act as a catalytically active site. And that is sort of the story everywhere. This is MnP-Sc3 ribbon X3, and X3 is X3 or A2 are active sites. X1 has a large absorption free energy, but in presence of one hydrogen at X1, you could have other sites which act as catalytically active sites. So that's how it goes. So the point here is that whether you have low H plus concentration or high H plus concentration, there are sites at the edges which are catalytically active. Okay. So what are the lessons from here? The lessons is that the edges provide active sites for hydrogen evolution reaction mechanism in these four systems. And that reminds us of work from Shaijimon's group in ISA Trivandrum, in which they were able to synthesize few layers of WS2 in a spiral structure. So if you are able to synthesize these materials in a spiral structure, you would be exposing a lot of these edge sites. So our question and suggestion for the experimentalists would be, can these trichalcogenides be synthesized in such spiral structures so that their catalytic efficiency can be increased even further? So I'm done with this. I think I'm right on time. So these are the people who were involved, who were and are involved in these studies. Khurshid Alam is a student of mine. Tishita is a postdoc. Rudra Banerjee was a visitor. And Sudeep Chakraborty is at IIT Indore. And finally, thank you very much for your attention.
Yeah, thank you, Prasenjit. I'm really glad your internet connection held out
so
long. Okay.
Yeah, so, we are lucky.
Yeah, so yeah, if anyone has questions, they could raise their hand or type it in the chat box. Yeah, while we're waiting for the other questions, I had one, Prasenjit. The thing is, so in principle, then the structures you've taken, you said that those were, you found a different set of compounds which had this high activity. So which had not been seen earlier, whereas in the other earlier examples, it was mainly the edge states which contributed. So if that is the case, then you said these structures didn't exist before. So are these some other polymorphs of those compounds?
Because no. These are compounds. These are not polymorphs of known compounds. I mean, so what I'm saying is the 13 compounds that seem to have the best delta GH values have not been reported in these layered structures, excuse me, in ICSD. Okay. So
there are reports of
I can't recall offhand if some of them exist in so more sort of three-dimensional structures, but definitely not in the layered structure. No, definitely not in the layered structure.
Because if there was the three-dimensional analog, then usually the rule of thumb is that you explore the other polymorphs of the same substance and see whether it falls within, some experimentalists quote 0.5 eV or something, because if the energy differences between them are very large, they may never form in this thing. So I was just wondering whether you had such numbers for these compounds.
No, we haven't compared with other polymorphs of these compounds, but as I said, we have compared with the isolated elemental solids of the three elements that form these compounds, and with respect to that, all of these are stable.
Yeah, there's
some of these other things we are exploring right now. Yes, I mean the more details of this. Yes.
Yeah, Venkatesh, can you unmute yourself and ask your question?
So thanks for your nice talk. So I want to know whether did you done phonon spectrum for these ribbon structures to confirm the stability of the your proposed structures.
Sorry, what is the quantity you asked about? I missed that point. To check stability.
If your structures are not stable, you may get negative frequencies in the phonon spectrum. So
phonon spectrum. That's exactly what we're doing now. That's exactly what we are doing now. And some of these, I mean, we haven't completed the whole series of compounds, but some of them we have, and they have turned out to be stable.
So ribbons are also stable. I mean, you mean to say? I mean, did you done the okay?
Yeah.
Okay. Thank you. Thank you.
Okay. So I don't think there are any other questions. So we thank Prasenjit again for a nice talk and move on to the next speaker, who's Ravichandran from IISc Bangalore. Prasenjit, you can stop sharing.
Yeah. Are you able to hear me? Hello? Am I audible?
Yes.
Okay, I will share my screen.
So I'll warn you at 20 minutes that you have 5 minutes of talk time left. Yeah, you can start.
Okay, yeah. So thanks for the opportunity to present my work at this conference. My name is Navneet Ravichandran. I am an assistant professor in the mechanical engineering department at IISc Bangalore. So today I'll talk about the work that I have done to develop a unified first principles computational framework to predict the phonon thermal and thermodynamic properties of semiconductor materials. So this work has been funded by these agencies, Boston College, the US Department of Energy, and Office of Nuclear Research, and a couple of graduate fellowships at Caltech and West University. So my research focus, just to give you a broad overview, is to develop new computational and experimental tools to probe the microscopic interactions among energy carriers in electrically insulating and semiconducting materials. So using these tools, I have worked on problems such as discovering new material candidates with extreme thermal properties. For example, here I'm showing a couple of pictures of new materials that we discovered using this framework. One of them is this boron arsenide single crystal. Another one is an isotopically engineered enriched form of boron nitride crystals, both of which have a thermal conductivity exceeding 1000 watt per meter Kelvin at room temperature. And I've also worked on experimentally probing interactions of heat carriers, in this case phonons, at nanoscale interfaces and boundaries. So you can find more information about these works in these papers. So in this talk, I will only focus on the computational materials discovery project to predict new material candidates with extreme thermal transport properties. So in these semiconducting materials, phonons, which are the eigenmodes of a perfectly periodic harmonic crystal lattice, are the main heat carriers. In fact, they control both thermal transport and thermodynamics. So these phonons have, as you may all know, have a characteristic phonon dispersion, which is a relation connecting the frequencies to the wave vector. You can define quantities such as the group velocity, the energy at which, the rate at which the energy is transported, which is given by just the slope of these curves. So these phonons in a real material also undergo interactions among themselves because no real material is perfectly harmonic, and they always have some inherent perturbative anharmonicities which drive these phonon-phonon scattering processes. So these phonon-phonon scattering processes can occur among 3 phonons at a time or 4 phonons at a time and so on. And a net total of all of these scattering processes can be summed up, that is the rate can be summed up to give a single quantity gamma, which is the total scattering rate. So knowing these properties like phonon frequencies, group velocities, and scattering rates, you can put them together into a kinetic theory expression to calculate the thermal conductivity of any material. So the expression here shows the thermal conductivity of a material is represented as a sum over all phonon modes in the crystal, that is the sum over the wave vector and sum over the polarization J. of heat capacity times velocity squared divided by the scattering rates. So as I mentioned earlier, phonons also control thermodynamics because they contribute to the vibrational component of the free energy. So if you know the free energy of a crystal, you can essentially calculate various thermodynamic quantities such as equilibrium lattice constant, thermal expansion, pressure, bulk modulus, etc. at finite temperature. So recent advances over the past 2 decades in first principles computational technique have enabled us to very accurately calculate these microscopic phonon properties and therefore the macroscopic thermal and thermodynamic quantities. So this first principles approach is predictive and it's free of any adjustable parameters. So to give you a quick overview of this first principles approach, all that we need to know to get the properties of a material is the crystal geometry, the types of atoms and the number of atoms that go into the crystal structure, and also a representation of the core and valence electrons in the crystal structure. That's it. So with just this information, we can crank it through the density functional theory machinery and calculate properties such as phonon frequencies, dispersion, the free energy, including the vibrational component, phonon scattering rates, and putting these all together, we can also calculate the total thermal conductivity of any material without any adjustable parameters. So in the red box on your left is one of the first examples of the work from my postdoctoral advisors group, where they use this density functional theory machinery to accurately predict the thermal conductivity of silicon and germanium over a broad temperature range without any adjustable parameters. So conventionally, this first principles approaches, people who have done these calculations typically restrict the calculation of free energy, that is the vibrational component of the free energy, to the harmonic term, and that's why this name quasi-harmonic. And also the thermal conductivity calculations are typically restricted to the case of interactions among 3 phonons only. So for the purpose of this talk, I will label this approach of using quasi-harmonic phonons and 3 phonon scattering processes as the conventional approach. So this conventional approach actually has been predictive beyond just silicon and germanium. For example, this is just a small list of the materials where the thermal conductivity has been predicted very accurately, thermal conductivity and thermodynamics, using this conventional approach. But naturally, at this point, a question arises. Is the conventional approach sufficient to describe the thermal and thermodynamic properties of all materials? So over the past 2 years, I have been developing a unified first principles framework, which includes higher order terms in the free energy and higher order interactions among phonons to answer this question, this precise question. Is conventional theory sufficient for all materials? In fact, using this for unified first principles approach extended beyond the conventional theory, I have worked on several interesting problems, such as predicting the ultra-high thermal conductivity of this new material boron arsenide, and as a consequence, a very unique non-monotonic pressure dependence of its thermal conductivity, and also found that the effect of higher order phonon scattering, for example, here 4 phonon scattering, that is scattering among 4 phonons, is actually quite strong and ubiquitous among a broad range of even common 3-5 semiconductors. So my work has led to identification of the ultra-high thermal conductivity form of boron nitride, that is C11 boron nitride, through isotopic purification. And finally, also extending the conventional theory to include higher order effects in phonon thermodynamics. For example, the case of strong phonon, anharmonic phonon renormalization in ionic crystal sodium chloride. So this is a broad overview of the work that I have done using this approach, but I'll only focus on this first topic in this talk. So the reason to go beyond the conventional theory and really develop this unified first principle framework was driven by a need to find high thermal conductivity material candidates. So as we all already know, diamond is the highest thermal conductivity material known to man. In fact, its thermal conductivity is more than 4 times higher than even metallic systems like copper and silver. So Glenn Slack in 1973 actually looked at all of these high thermal conductivity materials, that is thermal materials which have thermal conductivity more than say 300 to 400. And he found out several common features among these materials which give them the high thermal conductivity. So for example, if you look at the list on your left, all of these materials have very light constituent atoms. So we all know that when you have light atoms, you have high vibrational frequencies and high group velocities. And also, he also noticed that these materials have very simple crystal structure and very strong bonds, which means their anharmonicity, which drives phonon-phonon scattering, is also very weak. But as a surprise, in 2013, when Lindsay and co-workers did the calculations for several materials, they found out that their prediction using this conventional approach, that is with three-phonon theory, they found out that the thermal conductivity of boron arsenide can actually exceed that of diamond beyond room temperature. So notice that boron arsenide has almost 3 times higher average mass than that of diamond. So it is a heavier material than diamond, therefore defying conventional guidelines that I presented earlier in the previous slide. Yet their calculations using three-phonon theory, that is the conventional theory, predicted that the thermal conductivity is, could be higher than that of diamond. So before I go into my work on boron arsenide, let us first think about why boron arsenide's thermal conductivity is higher than diamond, even though the conventional guidelines predict the opposite trend. So to do that, let's go back and look at the thermal conductivity expression. And if you look at the phonon dispersion comparisons between diamond and boron arsenide, so because diamond is lighter, they have stiffer phonon frequencies, in which case the group velocity, which is the slope of these curves, is higher for diamond compared to boron arsenide. So clearly in the numerator for thermal conductivity, diamond wins over boron arsenide to get a higher weightage. But if you look at the denominator, that is the scattering rates, in this case the three-phonon scattering rates, what they found was that the three-phonon scattering rates for boron arsenide was unusually weak, almost 10 times weaker than that of diamond in this small frequency range. So this means that the denominator is smaller for boron arsenide than for diamond. So by having a smaller denominator, boron arsenide compensates for the smaller numerator, and eventually the thermal conductivity of boron arsenide even exceeds that of diamond at room temperature. So this shows that boron arsenide is achieving this high thermal conductivity in an unconventional manner, that is defying the conventional guidelines. So what causes this unusual weak three-phonon scattering rates in boron arsenide? Let's go back and think about it from the dispersion perspective. So here I am showing the dispersion, phonon dispersions for boron arsenide. You have 3 acoustic and 3 optic branches. And because the boron arsenide has a large mass ratio between boron and arsenic, you have a large gap in frequency separating the acoustic and the optic phonons. Now let's think about a typical 3-phonon scattering process where you have 2 acoustic phonons scattering into an optic phonon. So any scattering process has to satisfy 2 constraints. The first one being the conservation of momentum or the wave vector. I have chosen these 3 points such that this equation is trivially satisfied. You can see that Q1 plus Q2 roughly adds up to Q3, which is the x-axis. The second constraint is the conservation of energy. So what it says is that third phonons, the outgoing phonons energy should be equal to the sum of the incoming phonon energy. And in this case, because of the large gap between the acoustic and optic phonon, this process is completely forbidden. That is, you cannot find any 2 acoustic phonons that can scatter into an optic phonon. So this 3-phonon acoustic channel, acoustic optic scattering channel, which is actually one of the most dominant scattering channels in most other semiconductors, is completely forbidden in boron arsenide. So you remove one scattering channel completely from the picture, the total scattering rates go down, the denominator goes down, the thermal conductivity goes up. And that is the microscopic origin of why boron arsenide has such a high thermal conductivity, even comparable to that of diamond. So naturally, a question will arise at this point. What about higher order scattering involving more than 3 phonons? So clearly, you can see from this picture that if you add 1 more phonon to the mix, you can satisfy both momentum and energy conservation simultaneously. So at least from the constraints perspective, 4 phonons acoustic optic channel is allowed. But typically, scattering events involving large number of phonons is typically a higher order process in perturbation theory, and the strength of these higher order processes are expected to be weak. In fact, if you go back to the picture I showed you earlier, for the case of diamond, with just 3 phonon scattering calculations, they were able to achieve excellent quantitative agreement with the experimental data. So what this indicates is, in the case of diamond, 3 phonon scattering picture sufficiently describes thermal transport, and any addition of higher order scattering processes should not change this curve significantly. But the problem is with boron arsenide, it is not available in nature at that time. So they could not conclude whether the 4 phonon scattering processes are weak enough in boron arsenide or not. So the fundamental question that I wanted to address is to estimate or actually quantitatively calculate the effect of 4 phonon scattering on thermal conductivity of boron arsenide. So before I show you some results, let me just give you a flavor of how challenging this computational work is to calculate 4 phonon scattering. So the problem boils down to actually just calculating the scattering rates. So if you have the scattering rates including 4 phonon processes, you can eventually get the thermal conductivity with very little work. So this process can typically be broken down into 2 sections. The first one is to count the number of scattering channels that are allowed according to the energy and quasi-momentum conservation constraints. And once we have this list of allowed scattering channels, we can calculate the strength of each and every channel. This is where the anharmonicity of the crystal comes in, which describes the strength of each and every channel. And putting these two together, we can calculate the scattering rates through Fermi's golden rule. So if you look at a typical conventional approach calculation, that is calculation involving 3 phonons for a reasonable grid, I think these numbers are for a 21 cube grid in the Brillouin-Zor. You typically have about 100 million scattering events of 3 phonon processes, and to calculate and store the strength of these events, you typically require 150 gigabytes of storage. These kinds of numbers are very doable these days. You can get this work done on a single compute node in a matter of a couple of hours. But if you look at the corresponding numbers for 4 phonon scattering, the number of allowed events go up by 4 orders of magnitude, and the corresponding storage also increases significantly. So when I first implemented this code, the first version actually took me several weeks to get a converged thermal conductivity number. But over the past couple of years, I have implemented several symmetries of the matrix elements involved in the scattering rates, strength calculations, and also incorporated several hardware acceleration features to bring down the computational cost and the computational time to an order of 1 day. So having spent so much effort trying to improve the speed of the calculation, let's see if it's worth it or not. So here, just to refresh your memory, I'm showing the thermal conductivity of boron arsenide calculated using the 3 phonon conventional picture. So you can notice that at 300 Kelvin, the thermal conductivity exceeds 2000 watt per meter Kelvin. That is almost as high as diamond. If I include 4 phonon scattering, what happens is there's a dramatic decrease in the thermal conductivity from the 3 phonon value. In fact, at room temperature, you see that the thermal conductivity goes down by a factor of 2, and at higher temperature, it can go down by a factor of 5. So clearly, there is a significant drop and an effect of 4 phonon scattering on the thermal transport in boron arsenide. So before I proceed, if you remember, I had mentioned that for diamond, we expect 4 phonon scattering effect to be weak because we were able to get excellent agreement with the experiment with just the conventional 3 phonon approach. And that's basically what we get. When we did the calculation for diamond, including 4 phonon scattering, we hardly noticed any change in the calculated thermal conductivity. More importantly, we still got excellent agreement with the experiment over the broad temperature range. Okay, so now we have an algorithm or a first principles code with which we can calculate the properties of phonons very accurately. So with this code, we can actually go beyond just calculating thermal conductivity, right? So we can actually look at the microscopic origin of such a large reduction in thermal conductivity of boron arsenide. So to do this, let's go back to look at how the scattering rates compare between 3 phonon and 4 phonon processes. So once again, to refresh your memory, I'm showing the 3 phonon scattering rates of boron arsenide that I had calculated and shown earlier. So you can see that these phonons have very low 3-phonon scattering rates, and because scattering rates occur in the denominator, these phonons contribute the largest to the overall thermal conductivity with a 3-phonon picture. Now, if I add the 4-phonon scattering rates to this plot, you can see that 4-phonon scattering rates are the largest precisely in the frequency range where the 3-phonon scattering rates are weakest. So when you add these together through some kind of a Mathiassen's rule approach, you find that there is almost a 10-fold increase in the scattering rates at this lowest scattering rate point. So for example, if you see in this region, the blue triangles have been lifted up by a factor of I think 4 or 5 or 6 to these purple points. So there's a dramatic increase in the total scattering rates by addition of 4-phonon scattering. So the denominator is going up in this thermal conductivity expression, so the thermal conductivity is dropping down. And this is the microscopic origin for why 4-phonon scattering is having a dramatic effect on thermal conductivity. Okay, so these are just computations, right? So how do we know these things are actually happening in reality? So to confirm that, we collaborated with our experimental colleagues who fabricated, actually grew these crystals of boron arsenide for the first time in a very pristine manner with very few defects. And they were actually able to confirm our theoretical prediction. So the black curve that you see here is a calculation, black solid line is the calculation from our work, including both 3 and 4-phonon scattering for boron arsenide. And this curve lies very close to their best samples, which are shown by the red circles. In fact, around the same time, there were 2 other competing groups who were also trying to grow boron arsenide crystals, and their experiments are also confirming our theoretical prediction that the thermal conductivity of boron arsenide is strongly affected by 4-phonon scattering. If you look at this middle figure here, the blue curve is the 3-phonon prediction, and their experimental curves match or roughly match the red curve, both in rough magnitude and also in the trend. Sorry?
Just a sec.
Hello?
Yes.
Yeah, you have 5 minutes more of talk time.
Yeah. Okay, so one important point that I want to highlight is
मेरे पास तो support system नहीं आ रहा है यहाँ पे, about us आ रहा है.
Sorry, can someone mute her? Because
are you able to hear me?
About at
talk because someone is
about at because I'm not able to.
Yeah. Thanks. Yeah, please go ahead.
Yeah. So I just wanted to mention here that even though 4-phonon scattering is having such a large effect on the thermal conductivity of boron arsenide, the measured value in all 3 works is still exceeding 1000 watt per meter Kelvin. So to give you some perspective, silicon's thermal conductivity is only about 150 watt per meter Kelvin at room temperature. So this is about a 6-fold increase in the thermal conductivity. There's also independent work which shows that boron arsenide has similar electronic properties to that of silicon. So now you have a material which is as good an electronic material as silicon, but 6 times a better heat conductor than silicon. So you can really envision passively cooled electronic materials with these kinds of, with boron arsenide. So there are other materials also. So boron arsenide is not the only case where 4-phonon scattering is important. In fact, we have calculated the thermal conductivity, including 4-phonon scattering, for a broad range of materials spanning the entire III-5 family. And we find that a number of materials, 4-phonon scattering, that is beyond the conventional theory, is very important. As you can see in these pictures, the solid lines are my calculations in this new framework, unified framework, and the dashed lines are the conventional picture. And the experiments are really lying on top of the curve without any adjustable parameters. So it's a very predictive scheme, which includes the reality of having higher order effects in thermal transport. But there are also materials where the effect of 4-phonon scattering is weak. So we do find some of the III-5 compounds like boron phosphide, gallium arsenide, and silicon carbide, where the dashed and the solid lines are roughly overlapping or very close together, indicating that 3-phonon scattering, the conventional picture, is sufficient to describe thermal transport in these materials. So to give you a consolidated picture here, I'm plotting a histogram of the effect of 4-phonon scattering, that is K3 plus 4 divided by K3. And you can see at room temperature, all the III-5 compounds with the green bars have a very weak 4-phonon scattering. And there are a few candidates, including boron arsenide, which have extreme 4-phonon effect. Interestingly, we find that the candidates towards the right side, where the 4-phonon effect is weak, include BCN compounds. What I mean by that is these compounds are composed of boron, carbon, and nitrogen on some other atom. And with this insight, we actually found out that by isotopically enriching boron nitride, the thermal conductivity could be significantly enhanced. So our calculations showed that the thermal conductivity of boron nitride, if isotopically enriched, can go up by a factor of 2.5. And we communicated this with our experimental colleagues, who were once again able to prove that our predictions are right. So all these different curves are different calculations involving both 3 and 4-phonon scattering for different isotopic compositions. For example, the green one is natural boron nitride and the red one is C10 boron nitride. And you can see that the experiments are running on top of the theory. More importantly, the achieved thermal conductivity in the experiment is roughly 1800 watt per meter Kelvin at room temperature. To give you some context, diamond's thermal conductivity is around 2000 for the naturally occurring diamond. So this is quite comparable to that of diamond. So I'll just take a couple of minutes to show how we are able to even capture the failures of the conventional theory for thermodynamics as well. So in weakly bonded materials like sodium chloride, which is an ionic crystal, when you do the conventional quasi-harmonic approximation for the free energy, you see that the lattice constants are significantly over-predicted compared to the experiment. In the thermal conductivity also, if you do the full calculation, including 3 and 4-phonon scattering, the conductivities are much lower than the experimental measurements. And we found out, interestingly, that this failure of this conventional theory on thermodynamics is more fundamental in the sense that the phonon quasi-particle picture is itself breaking down. So for a phonon quasi-particle picture to work, gamma or omega should be much smaller than 1, gamma being the scattering rate and omega being the frequency. You can see that around 500 Kelvin, this assumption is broken down. So we developed a self-consistent renormalization framework to fix this issue. This renormalization scheme was based on this loop diagram that I think you're all familiar with. And when we included this renormalization, we not only got excellent agreement with the experiments for lattice constants, the phonon quasi-particle picture is now well behaved. Gamma or omega is much lower than 1 for most phonons. And the thermal conductivity that we get, that is the red solid curve on the figure on your right, lies very close to the experimental data. So to summarize, I hope I have shown you the very predictive feature of this unified first principles framework, which includes both the lowest order conventional approach and higher order effects on phonon scattering and thermodynamics. And using this framework, I have worked on several problems involving materials discovery for energy transport. I also, as I introduced in the first slide, I also do some experiments, but for the interest of time, I won't be able to go into this. So yeah, thanks for your attention. I'd be happy to take any questions.
Yeah, thanks for a very nice talk. I think Shobna has raised her hand for a question. So Shobna, can you unmute yourself? And
yeah, thanks. That's very interesting work and great talk. I was just wondering, so you showed that 4-phonon processes are very important. Do you have any idea about why they contribute so much? Is it mostly because of the sort of joint density of states effect, or is it because of the matrix elements, or is it because of both?
It's a very good question. Let me see if I have a backup slide for that. Yeah, so by joint density of states, I'm assuming you mean this phase space, right? The number of
yeah, exactly. Right? Yeah.
Right? So in whichever material we find 4-phonon scattering to be important, there's always a weak 3-phonon scattering phase space. So the lowest order scattering.
Sorry, can you repeat the last sentence again?
So in any material where we find a strong effect of 4-phonon scattering in strongly bonded materials like 3,5 compounds, we always find a weak 3-phonon phase space.
Okay.
So there is the lowest order scattering is weak because of some features in the dispersion and joint density of states. Okay. And 4-phonon scattering just because of sheer combinatorics does not get affected by the features of the dispersion.
Yeah.
So whenever you have, for example, a large mass ratio, you have a large AO gap that basically removes one channel, AAO, that is 2 acoustic and 1 optic channel, and that exposes other features in the dispersion. So eventually you get very weak 3-phonon scattering rates, and then 4-phonon scattering becomes comparable.
So it's mostly a phase space effect then.
In strongly bonded materials, in the case of sodium chloride that I showed at the end, it's a combination of both.
Okay.
It's both strongly anharmonic, and there is some phase space effect.
Okay, thank you.
Yeah.
Yeah. I think Arindam has a question. So Arindam, please unmute yourself.
All right. Thanks, Priya. Navneet, this is a really interesting talk. This is Arindam from ISC Bangalore.
Hi, yeah.
Hi. So I have a very short question. So this is regarding this phonon scattering, or even in conventional picture. These are all in the diffusive regime, if I understand correctly. And so what is your take on the importance of 4-phonon scattering as you start going down in the size of the sample? Suppose something goes down to in the order less than or close to the typical, the phonon mean free path.
Yeah, thanks. That was a good question. So yeah, right. If you take a very thin material sample, for example, you will have boundary scattering. So this 4-phonon scattering is actually can be treated on the same quote-unquote footing as 3-phonon scattering, in the sense that you can calculate an effective mean free path combining both 3-phonon and 4-phonon scattering rates. And if that mean free path is comparable to your system dimension, then the diffusive scattering becomes at the boundary becomes important. So it's really a comparison between the length scale of your sample, temperature as another variable, and the material that you are using.
Okay, so you mean to say there is, the boundary determines the scale, and essentially the 4-phonon scattering is no longer.
That really depends on the material and temperature, right? If you go to low temperatures, and if you take like diamond, the mean free path is several millimeters long. So, but if you take sodium chloride at 600 Kelvin, the mean free path is a few nanometers.
Right.
So yeah, right. So if your device is comparable to that mean free path, it will be affected by diffuse scattering at the boundary.
Good. Thank you.
Yeah.
Yeah. I had a naive question. Since there are no other questions, let me ask it. Essentially, at least from your results on boron nitride, I think you can't, without a calculation and without getting your phonon spectrum, you won't be able to say whether your 3-phonon or 4-phonon processes would be important. I mean, there are no naive rules which you can take.
Yeah, so that was the motivation for this work. We wanted to get some insight just by looking at the phonon dispersions, whether we can predict a material will have strong 4-phonon effect or not. So this paper contains these selection rules that is related to the joint density of states, and you can identify based on just the dispersion which of these scattering channels will have anomalously weak joint density of states. What we find is in the case of 4-phonon scattering, the joint density of states is not sensitive to the specific features in the phonon dispersion. And additionally, we find that materials containing boron, carbon, and nitrogen atoms typically have weak anharmonicity. So with these 3 ground rules, we will be able to kind of predict this plot, for example. So if you look at the left-hand side, aluminum antimonite is a very large mass ratio compound, does not contain boron, nitrogen, or carbon. So you would expect with these rules that the effect of 4-phonon scattering will be strong. So it will give you a good picture, but of course, if you want to get very quantitative results, you have to do the full calculation.
Sure. Okay. Okay. Thank you very much.
Thank you.
So, yeah. So we now move to the next talk, which is, I think, a contributed talk. Can you stop sharing so that, yeah. Oops. Yeah, it's by Shubhajit Jana. He's going to be talking about ultraviolet photodetectors using chemically synthesized.
Hello, ma'am. Can you hear?
Yeah, I can hear you. I'll tell you after 10
hello,
minutes.
Hello, ma'am. Can you hear me?
Yes, I can hear you. So I'll tell you after 10 minutes that you have 2 minutes of talk time left, so that, yeah, you can plan.
So, yeah, good morning and hello, everyone. So I am Shubhajit Jana from IIT Kharagpur. So I am right now at my village, so I have very poor internet connection. So Sreosidas is sharing the computer screen on behalf of me. So I will ask her to change the slides in between. So the title of my talk is ultraviolet photodetector using chemically synthesized phosphorine nanocrystals, where I will talk about the phosphorine nanocrystals and their synthesis and application as a photodetector. Next slide. So in introduction of optoelectronic device, so optoelectronic device is any electronic device that utilizes the effect of light radiation. So in our everyday life, we have many optoelectronic devices surrounding us, like solar cell, LEDs, photodetectors, etc. So they have very good spatial resolution, better sensitivity, and in case of communication, they have better speed. So to make a device much more compact and to increase the integration density, there is constant efforts to minimize the material used, minimize the surface area of the material used. So in this case, the two-dimensional materials are very important here. So next slide. So two-dimensional materials are materials where atoms are arranged in a plane. So ideally, it should be one atomic thickness, and graphene is the ideal 2D materials, and it is the mother of all 2D materials. So these two scientists, Andrei Geim and Novoselov, they were awarded Nobel Prize in 2010 for their discovery. So graphene has the strongest, graphene is the strongest and thinnest material available till date, but it has no band gap. So that's why it has no use in optoelectronic devices other than interconnect. So in search for alternative 2D materials, people came up with transition metal dichalcogenates, but they have indirect band gap in bulk form, and only in monolayer form they have direct band gap. So in alternative 2D materials, black phosphorus came that 2D phosphorine has direct band gap irrespective of its layer number. So it has two directions, in anisotropic direction like zigzag and armchair direction. It has band gap of 0.3 in bulk and 1.5 electron volt in monolayer form. So it exactly bridges the gap between TMDs and graphene. So my talk is based on this phosphorine nanocrystals, what we have synthesized in our lab and applied it. So next slide. So we have synthesized these phosphorine nanocrystals in a controlled manner. So in a nitrogen atmosphere. So after successful sonication for 5 hours through probe sonication, the Hello, can you hear me? Hello. Hello, ma'am. So, hello. Should I continue? Hello.
Yes, we can hear you. Please continue.
Okay. So after the successful exfoliation, we have centrifuged at different speeds like 1500 RPM, 5000, 10,000, and 15,000 RPM. So we have given the sample name as sample A, B, C, and D respectively. So after this microscopic analysis like HRT, and atomic force microscopy, we have found out that the nanoflakes have average size of 400 nanometers, and sample B, C, D, they are essentially nanocrystals of average size of 5.5 nanometers, 4.5 nanometers, and 2.5 nanometers respectively. Next slide. So we have next slide. Yeah. So we have then characterized it using structural and chemical stoichiometry using this XRD and Raman spectroscopy. So in XRD, we can see that I have compared this various sample XRD spectrum with bulk. As the sample crystalline size goes down, we can see the XRD peak has diminished intensity, and also the peak has broadened a bit. So that is due to the reduced crystalline size in nanocrystals. Again, in our Raman spectra in figure 2, we have compared these results in comparison to bulk. So as the all the samples have shown these three characteristics peaks, where the AG2 peak, this is the characteristic peak for 2D black phosphorus. So in case of any size reduction, so this is the mode is maximum sensitivity. So we have found out that this AG2 mode for sample D, which is the smallest size nanocrystals, have suffered maximum 2 centimeter inverse of Raman shift. So these two experiments suggest that the retained crystallinity of the exfoliated black phosphorus nanocrystals. So next slide. So yeah, we have then characterized using optical spectroscopy like absorption and photoluminescence spectroscopy. In absorption spectroscopy in figure 1, we can clearly see the broad absorption from all the samples. So in also they have most I mean they have a broad absorption, but their main peak is around 400 to 500 of nanometers. But as the nanocrystal size goes down from sample A to D, we have found out that there is a blue shift, which is in accordance with the quantum confinement effects. In figure 2, I have represented this photoluminescence spectra with an excitation of 3 to 5 nanometer laser excitation. So three clear peaks are observable at 400, 440, and 500 nanometers approximately. But if you look it closely, so you can see there is another higher wavelength contribution. So upon deconvolution in figure 3, we have found out that yes, there is another higher wavelength component at around 580 nanometers. So the origin of these peaks can be explained using and the band diagram represented in figure 4, where the radiative surface states contribute to this higher wavelength emission. So black phosphorus is the most stable form of phosphorus, but still it gets oxidized whenever it comes in close contact with humid atmosphere. So they contribute a lots of oxygenous functional groups at the broken phosphorus bonds to passivate them. Okay, so next slide. So yeah, to know the exact role of different functional groups, so we have performed time dependent temperature dependent photoluminescence spectra for nanocrystal sample B, C, and D. So for the nanocrystal sample B, C, and D. So sample B and C has shown positive thermal quenching behavior, but sample D has shown negative thermal quenching behavior. So sample what is positive thermal quenching behavior? So with increase in temperature, increased rate of non-radiative recombination is known as positive thermal quenching behavior. That is because as the temperature increases, there is increase in non-radiative recombination, so that decreases the PL intensity as we increase the temperature. But for sample D, we have seen the opposite. As you increase the temperature, so the PL intensity has increased. So to explain that, we have to take help of this band diagram in figure 4. So where, as I said, the sample D contains smallest size nanocrystals, where smallest size nanocrystals where there it has the highest surface to volume ratio. So there are lots of functional groups attached to its surfaces, so they contribute a lots of intermediate states. So they trap the electrons so while transiting from LUMO to HOMO band. But in lower temperatures, the detrapping is not allowed. So as the temperature raised, they get enough energy and they get activated and they transit radiatively. So they increase the photoluminescence intensity at higher temperature. So the NTQ PTQ characteristics can be explained using this equation by Shibata et al, where the denominator explains positive thermal quenching and numerator explains negative thermal quenching. So next slide. So using this equation, we can feed the integrated PL intensity with inverse of temperature to see the exact NTQ, PTQ characteristics with their extracted activation energies of different radiative and non-radiative states. Next slide. So we have performed these XPS measurements to know the chemical states of the phosphorus and oxygen groups. So we can see as along with this phosphorus 2p doublets, there is another higher energy oxidized phosphorus band EXOY. That is how I have represented it. So as we can see in comparison to sample B and C, sample D has a stronger oxygenous band. So from the table 1, we have extracted out that oxygenous phosphorus contribution, and we can see the sample D has almost 50% of the phosphorus has been oxidized. So that is why it is showing this negative thermal quenching behavior. So it has the, as I said, it has the largest surface to volume ratio. So it has the largest density of these functional groups. Next slide. So then we have used these phosphorus nanocrystals to show the potential application. So we have spin coated the sample over SiO2 substrate, and then gold top electrodes were taken by thermal evaporation technique. So then from figure 2, we can see that it has a moderate photo to dark current ratio of 16 and responsivity of 0.2 amperes per watt at -2 volt bias. So while the excitation was used 3 to 5 nanometer UV laser. So next slide. Yeah, next slide. Yeah. So in this slide, I have shown that different device performance of different nanocrystal samples. So from figure 1, we can see that sample BCD, the photo current of the various devices using sample B, C, and D. So as you can clearly see, sample B has highest photocurrent, sample D has the lowest photocurrent. So that is because sample D contains lots of surface traps, so they recombine the photo generated electrons and holes. So that's why the photocurrent is very less. From figure 2, we can also clearly see the temporal modulation of these of the various devices. So sample B has shown the highest modulation index, that is due to its highest photocurrent. From figure 3, we have used bias dependent temporal modulation. So as the bias increases, the photocurrent, generation of photo electron and hole increases. So it increases the photocurrent in our external circuit. So the response time is presented in figure 4, where we have found that the response time of this device with sample B is almost around 2 to 7 milliseconds. Yeah, 2 to 7 milliseconds. So all the excitation used was a 3 to 5 helium cadmium UV laser. So next slide. Yeah, so in summary, we have successfully synthesized black phosphorin nanocrystals using a simple sonochemical method. So we have employed these phosphorin nanocrystals in a photo detector device. So it is basically UV photo detector, where the excitation was, detection was used using 3 to 5 nanometer laser excitation. So the bigger size nanocrystals have shown normal thermal quenching behavior, but smallest size nanocrystals have shown negative thermal quenching behavior, that is attributed to the attachment of various surface functional groups, oxygenous surface functional groups. Yeah, next slide. So next. Yeah, I finally thank my supervisors, Dr. Sivakiran Bhakta and Professor Sumit Rai, for their constant help and encouragement and motivation. Finally, research facilities at IIT Kharagpur and central research facilities and microscience lab. So in this group picture, I have encircled my face. So finally, thank these organizers of this QMAT conference. This is a very nice conference for learners like us. So it has been a good platform to learn various things in these crucial times. So I finally thank everyone for listening and having patience because I have very poor internet connectivity. So I am using my mobile right now. So yeah, thank you all. I'm done. Yeah, hello, ma'am. Hello, ma'am.
Priya,
hello,
are you there, Priya?
Yeah, I'm done. I have completed my.
I'm sorry, I had muted myself. I'm sorry. Okay. Yeah. So thank you for a nice talk. And yeah, I see that there are no questions. So thank you very much. So we'll move on to the last talk of the session.
Okay. Okay. Thank you.
Can you stop sharing so that Devjani, are you there? Can you share your screen? Devjani, we can't hear you. Or am I audible?
Yes, you are audible.
Okay, fine. Okay. Devjani, we can't hear you. Can you unmute yourself? Maybe you're muted.
Yeah, you're audible. Am I audible?
Only now. Yeah. Okay. So I'll warn you at 10 minutes that you have 2 minutes of talk time left. Sorry, again, we can't hear you.
Am I audible?
Seems to be some problem with your connection.
Hello, Devjani, please switch off your video. You have some internet issue, I think.
Hello.
Best would be if she logs out and comes back in.
Can you try that? Yeah.
So is it visible? So I'm unable to understand that whether I am audible or not.
Devjani, you are audible. Only your voice is sometimes breaking.
Okay. Okay, then I am just starting. You just point me out that whenever I am not audible. Okay, Tanushree?
Yeah, please.
Okay, okay. Thank you so much. So, so I will talk today about the correlated attributes at bimetallic nanostructures. So I am Devjani Karmakar from BARC, and first let me thank the organizers for giving me an opportunity to talk here. And, next is I'm just so this is I'm starting with some statutory warning that my Wi-Fi connectivity is very poor, so I may sync anytime. So please excuse me for that situation. So I start with the acknowledgement, and I will today talk about this paper, which is in physical chemistry, chemical physics, has just appeared. It's on AUAG nanostructure. And this is Tuhin Kumar Majhi, who is the first author of this paper. He has participated in the DFT calculation. Kumar Vaibhav, he has helped in parallelization and shading of the transport properties and transport code. And also Ranjit and Adarsh and Samir, they have participated in active discussions. And this is a collaboration work. And I should also thank the Anupam Supercomputing Facility and discussion from Arindam Ghosh, Manish Jain, so Vik Datta, Kanti.
At least for me, you're breaking. I don't know about the others. I can't hear you.
Yeah, for me also.
It's breaking.
Do you have some other connection through your phone, for instance?
Actually, I can't hear her at all now.
Yeah, same here. I can just hear some beats.
Yes, some binary coded messages coming.
Devjani, we can't hear you.
Hi.
Maybe she also can't hear us.
Okay. Somehow today seems to be the day when we are plagued with these internet issues. It started with our chairperson of the session not being able to connect.
So the chair can be blamed.
The present chair or the...
I think the internet gods don't like women scientists.
Yeah, it was...
Shobhana, Shobhana, don't start that.
Well, Prasenjit Sen was the one who contacted me first, saying that our internet is like in a bad shape at HRI.
Yeah, but see, there was no problem for his talk.
And there's no problem.
No, but
all of us hearing you, Shobhana.
I use my mobile connection. I mean, the internet was still off.
No, but see, women chair for the session, women speakers.
Well, you can hear me.
Maybe you should ask the speaker to log out altogether,
you should only
log
have
back
women
in.
audience also.
That's very vocal and we can hear loud and clear.
What?
I could hear Didi's comment here. so shall I start now? Actually, my Wi-Fi connectivity is horrible, actually.
Do you have some other one, like your hotspot from your phone? That seems to be more reliable these days than...
No, I am in BRC colony and no hotspots are allowed inside except MTNL. And okay, let me just start.
Yeah, go ahead.
Now it is audible, right?
Yes,
it's audible now, right?
Yes, yes.
Okay, so so I was kind of motivated for all of these 9 papers, which was distributed over a period of 9 months, which are 2 theoretical and 7 experimental, and all dealt with a specific metal combination AU and AG. The key experimental results were the resistive transition, onset of diamagnetism, and suppression of localized surface plasmon resonance. The experimental systems are embedded structures, large area interfaces, doped and implanted films. So, U and AG, we all know that these are noble metals are having the normal Fermi liquid nature and having parabolic band, and they are having the FCC lattice structure, and this is the regular.
I think again, Jenny, there's...
Maybe you can email your slides to the admin. They can just flash it and you can give your...
Yes, ma'am, we can do that.
Jenny,
Look at the normal that there is...
Jenny, we can't hear you. It's again the same.
Okay. Am I audible now?
Yeah, but it's just coming in patches. One other suggestion is we can put you as the last talk tomorrow. So what you can do is send a recorded version and you can, connect via phone or something so that you're just, you can answer questions like that, whereas we play your version. So after we can tell you the exact time. So send us a recorded version of your talk. That would be better because, it holds for 1 minute, then again goes away. So I think, is that fine? Did you hear me? Could you hear me?
I don't think she's there.
Yeah, I don't have her number. Can someone who has her number call her and suggest
Yeah,
this?
I'll call her. I'll call her.
Again,
she is busy.
Bimetallic FCC nanostructure. This is a perfect example of metamaterials.
We cannot hear you in between. We lost you.
Yeah, this last slide I am starting. Again, I got disconnected. So I am starting.
Suggesting is because we can typically see you for one slide and then it goes away. So what you send us a recorded version of your talk and we'll send you the slot where we're putting you in. And then you can answer questions via phone or something like that. That should be better because...
Let me try once more. Right now the lights are whatever that Wi-Fi lights are showing me some stability and I'm just trying.
Okay.
So these are the bimetallic FCC heterostructures, which are perfect example of metamaterials when two different kind of materials are combined together and giving some very different properties. So what we have done is we have tried with this AG111 surface, AU111 surface, and AU-AG large area interface, and then embedded nanostructure, and then AG-doped AU nanostructure. All of them belong to a hexagonal Brillouin zone. And the next slide, I will be showing the band dispersion along this path, gamma X, Y, gamma. And we have treated all this system by using some single particle derived approaches, which are DFT and GGA-PBs and plus spin-orbitally coupled that mechanism. And also, I must mention here that we have taken care of all scalar relativistic corrections here. And also for a small model system, we have checked all class U and hybrid functional calculation, so that we can tell that this GGA-PBA calculation, whatever we have done for this system, is a stable calculation. So next part is that we have done some time-dependent DFT calculation. Phonon calculations were done, and then DFT coupled quantum transport. All are single particle derived approaches. And for FCC bimetallic heterostructure, if you just look at the orbital projected fat bands here, so these are AG and AU111 system, and then you can see that near Fermi level, that for AG it is PD hybridized levels, and near AU it is SD hybridized levels. And if you are making a large area interface between these two systems, then you can see that there are large amount of charge transfer from AU111 to AG111, so that there is a increase of curvature of the band structure near the Fermi level, and there is a reduction of so there will be a corresponding reduction of the carrier effective mass. But if you are going for the embedded and doped systems, you can see here there is some kind of localization of the carrier which is happening for certain part of the Brillouin zone, and you can see from X to Y there is a kind of carrier localization here. And for these AG doped AU surface, there is in fact there is a localization here, and also there is a band inversion here. So with small amount of fluctuation within the system, you will be able to open a gap here, and there can be a flat band kind of more effective mass carrier localization present in the system. So now whenever we see here that we have calculated the effective mass for this system, when we have calculated that, we have seen that here AU and AG, these are the effective mass. For AU-AG111, you can see that there is a reduction of effective mass. So there was some earlier this data for this AU-AG large area interfacial system by Satish Ogle and others. They have shown that there is no advent of any kind of correlative behavior for these kind of systems. That is quite understandable, because all the bands here are having simply Fermi liquid nature. And for the embedded and doped systems, there is some localization of carrier indication, and you can see here that in comparison to AU and AG111 surface, there is for embedded and doped system, there is a increase of effective mass. So there is one order of magnitude increase. And don't look at this plasma frequency stuff. I'm explaining it afterwards. And so next we have calculated the Fermi surfaces for all those three systems, and there I will be uttering some term like CDW. So that CDW of Rudolf Wells at 1930 for one-dimensional chain of one electron atoms, which is having a fundamental instability, where such kind of dimerization occurs, and there is a gain in electronic energy that exceeds the cost of this restructuring. And because of that, there is a metal to insulated transition in this system, which opens up a gap at the Brillouin zone. And that happens at a critical temperature, TCDW. So that is the CDW transition temperature. And in 1959, Walter Kohn has pointed out that there is a nesting driven phonon softening at Q equal to 2K.
We again have lost. You're again inaudible. Debjani, we can't hear you again. Am I muted?
No, we can hear you.
Okay. No. Okay. I guess.
Debjani, we cannot hear you. Yeah, again you got, I think your internet broke down again. Oh, even her phone is not working, looks like.
So I guess I think we should. I think we'll email you about a new slot. We'll ask her to send a recorded version so that it doesn't have to depend on her internet, and we'll send a mail around about the details.
Okay, so Deblina has said that she has given her email ID to Debjani, and if she wants, she can send the slides and the recorded thing.
Yeah, so we'll send a mail around, because otherwise the next session again would be delayed. So I think we'll schedule her as the last talk tomorrow or something like that. So,
okay.
Because otherwise it's, I mean, we'll be listening to the same thing again and again, I think so. Yeah, Debjani.
Yeah. I think I'm back again, but I am trying to finish it off. Actually,
you want to finish it? Because I think it's better you send us a recorded version. There's a slot available tomorrow.
There. Any of your voices, I don't know that whether I am what I am doing. Anyway, there is a one-dimensional change of chain of sodium atoms. What they have taken that Johannes and Margin, and they have shown that even for after incorporation of good relaxation, these kind of divergence, logarithmic divergence, that breaks. So for a non-ideal one-dimensional system, there is a very poor kind of logarithmic divergence, and even for 2D and 3D system, that thing does not work. So there are three types of CDW ultimately. One is just where a quasi 2D system where that Fermi surface nesting drives the EPC, that is the electron phonon coupling. Another is type 2 CDW, which was driven by electron phonon coupling and not by Fermi surface nesting. And there is a type 3 CDW where there is a charge order present within the system, and there is no indication that FSN or EPC is the driving force for that charge order. So what we have done here, actually, we have calculated that AUAG111 surface for an embedded and AG.AU. We have calculated the Fermi surfaces, and we have shown here that there are, for AUAG111, there are hole pockets at the center, and that there are two kinds of nesting vector, one towards the mid side of the hexagon, another is towards the corner of the hexagon. And that's why whenever we are looking at the Fermi surface here, that those are partial nesting. They are a very small electron pockets here. So this is not a potential candidate for having the Fermi surface nesting. Rather, the embedded and doped system, those are having more complete nesting. And then if you can look at the calculated nesting vectors, then they are having a kind of incommensurate nature. Those are differing from the A. So that is the lattice parameter. So that means that there are these two are the potential candidates where one can have a CDW kind of variation, instability. So next is our TDDFT formulation, where we have done a full response function, and then that full response function is calculated from the non-interacting response function and with the frequency-dependent dynamical exchange correlation kernel. This is the dynamical EELS, which we have calculated, that is the electron energy loss spectra, that gives us some idea about the plasma frequency. And also we have calculated the intraband effects. Since these are all metallic systems, one has to take care of intraband effects in addition to the interband effects. And if you look at this intraband effect, then you will be seeing that there is a plasma frequency sitting here, which is actually inversely proportional to the effective mass. And if you are calculating the real part and imaginary part of this epsilon here, then it is having a negative divergence here, and that is having a positive divergence here. That should happen if it is a root system. But and also these are a potential ENZ material, that is epsilon near zero material. So if epsilon tends to zero, then from this simple relation that n also should tend to zero, and from the Snell's law, but if n1 tends to zero, then theta 2 tends to zero, and vice versa. So emission and absorption of light, that should be normal to the surface. So this system can have a potential use in optical interconnectors, and also there are that if you look at this data and just have a simple, just simply differentiate this system, that this equation, then you will be seeing here that this delta n for epsilon tends to 0 will be very high. That implies the onset of strong non-linearity in the system for those frequencies for which we will be having the ENZ behavior. Now, if we look at this thing, for all these three systems, you will be having this root kind of behavior where there is a negative divergence and there is a positive divergence. And look at the electron energy loss spectrum, there are intraband plasmons present in the system. But these two last systems, there are epsilon non-zero, that near zero behavior, epsilon near zero behavior for UV-vis energy range. That is from starting from UV energy range to visible energy range. There is a near zero epsilon behavior present in the system, and also all kinds of low energy intraband plasmons are frozen for these things. And so there is an interband plasmon peak only present here. So we are having a flat band induced NFL nature here, presence of localized area, reduction of plasma frequency that I'll be showing in the table. And then there is a epsilon near zero behavior near the UV-vis range. And if you look at the plasma frequency here, there is an order of magnitude decrease for the plasma frequency. As I have told you, that plasma frequency is having a inverse proportionality with the effective mass. Now, next we have calculated the phonon instability for AUAG and AUAG dope systems, where it shows that there is a presence of soft phonon within the system that actually shows that there are instabilities present in this system. But it is not known whether these instabilities are from the structural instability or it is from the CDW kind of charge instability. And when we have calculated the electron phonon coupling constant, that has shown a very interesting result, that whenever you are looking at that AU111 and AV111, then whatever is the electron phonon coupling constant, there is a 1 order of magnitude change for AUAG doped system. Now, next is that our DFT coupled quantum transport. I am not describing it here, but what we can show here, that even for the simplest possible device here, that is AG channel and AU contact, and the reverse, that AU channel and AG contact. So for those kind of systems, we have calculated that we have calculated the IV characteristics and also the local dose. If you look at the local dose of this system, that this is the one-dimensional local dose, that will be showing you that near the interfacial region for AG channel system, there is a large interfacial scattering present. And whenever you are taking that transmission color map, whenever we will be taking it, then you can see that for the system, these transmission color maps, those are calculated perpendicular to the transport axis. So there are pockets which are very much inhomogeneous. For AG channel system, these are very much inhomogeneous, and there are highly transmitting pockets here. So even for the best possible devices in this simplest possible devices within this system, so there are inhomogeneities, large amount of inhomogeneities present within the system. So that I can
you have 2 minutes to wind up.
With that, we can conclude here that for these kind of systems where nanostructure, there are interesting nanostructural morphologies. We are having localized orbital chemistry, higher carrier effective mass, prediction of FSN-induced instability, that near zero epsilon behavior, and suppression of interband plasmonics and complex quantum transport to highlight the fact that for selective nanostructural morphologies, that localized orbital chemistry that may lead to exotic electronic properties which are widely different from the individual compounds. So this is a kind of having interdisciplinary interest, which is connecting physical chemistry to physics and material science and more. So at the end, I will thank you everybody for your patience. I am very, very sorry for my Wi-Fi connectivity, extremely sorry for that. And also hope for a normalization for my QMAT 4. And I'm really missing this kind of this kind of atmosphere of conference.
Thank you, Debjani, for a nice talk, despite all the difficulties. Okay, so I don't know whether
I have a short question.
Yeah, Bhaskar, please.
Debjani, very nice talk. Can you identify in real space some like decoupled silver chain or gold chain embedded the other material?
So Bhaskaran, I could not hear properly. If I have understood that whether I can do it for a linear chain compound, is that your question?
No. If in your structure, can you identify some isolated silver or gold chain which is leading to this one-dimensional bands? Can you identify structurally?
No, we have not tried identifying structurally the isolated stuff. But since you have prescribed some such things, I will go back and find out in my data that if I can actually find it out some isolated stuffs.
Okay, I will contact you by email. Thank you very much.
Definitely, I will try to.
Okay, so as there are no more questions, then we'd like to thank Debjani for surviving this internet problems.
Yes, horrible internet. Thank you, Priya, for sharing my.
And thanks everybody for sitting through it. Thank you. Yeah. So the session is over, and we meet again at 12:05 for the next session.